Okay, 4.3, covalent structures. Now, there's quite a bit in this topic, but today our only focus will be on determining the molecular shape of molecules. Molecular shapes. To determine the molecular shape of a molecule, we use what's called the VSEPR model. That's how we pronounce it, VSEPR. I'll always remember one of the questions on my first chemistry test was, what does VSEPR stand for? And I could not remember it. I did not get that right. But if you understand what VSEPR stands for, what it's an acronym for, it really helps with this. So see if you can remember, think back last year, you learned it. What does that stand for? It stands for valence shell electron pair repulsion. And if you understand what that means, it really helps with what we'll be doing. So valence shell electrons, of course, those are the valence electrons responsible for the bonding between atoms, and not just the bonding between the atoms, but the lone pairs around the atoms. So electrons always come in pairs, whether it's a shared pair or a lone pair. And because they're negatively charged, they repel each other. So valence shell electron pair repulsion simply means that all of the pairs of electrons around an atom will get as far away from each other as possible. And we use the VSEPR model to predict molecular shape, molecular polarity, not bond polarity, but the polarity of the entire molecule, and bond angles. There are 5 basic shapes that you're responsible for in standard level IB. When you get to IB higher level, IB Chem 2, there will be more complex shapes, but these are the only 5 you're responsible for. And you don't need to write these down. I'm going to show you how to draw these in just a second. Linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. I'm going to show you a handwritten video on how to best draw these shapes. But before I do that, I want to show you this simulator. You're going to be using this after you take the notes to do a little virtual lab. This is a PhET simulation. And let me go to full screen here. And it's pretty cool. Now we're going to be using the model here. You can play around with the real molecules later. All right, now how this works, again, you're going to be turned loose on this. This is our central atom. It's all generic. You can't identify a particular atom. So this is our central atom. So we're limited to the molecule. We can't build a molecule more complex than just one atom with stuff bonded to it. We have single bond possibility, double bond, triple bond, or a lone pair. Now, as you can see right now, we just have 2 bonds to a central atom. And you can see that they are as far away from each other as possible. Now you can see I can kind of play around with it a little bit, but left to its own device, it will arrange itself so that the electron pairs get as far away from each other as possible. Now let's say I put in a lone pair. Well, it's going to go on, and all this will go on to the central atom. So you can see now that we have this shape. It's really cool. You can kind of rotate it around, see what it would look like in 3 dimensions. Now, when we draw the shape, we only draw the bonds. We don't include the lone pair. But we need to know that the lone pair is there to understand the shape. Without the lone pair, and you can, the little X's over here is how you remove it, you can see that it would be linear. But with the lone pair, it's going to be, the shape is called bent. Now down here, I can click on this little box, molecular geometry, and it'll say bent. So that's the shape, bent. Now if I put in another lone pair, it would still be bent. In the notes you're about to take, the handwritten notes I'm going to show you, I'll show you the distinction between one lone pair or 2 lone pairs for the bent shape. But let me get rid of those. Okay, let's say that I had another bond. Now you can see that this, and the example that I'm going to show you in the notes is boron trihydride. Remember, boron only has 3 pairs of electrons around it. There's no lone pair. This shape is called trigonal planar. And you can see trigonal because it's like 3 points of a triangle. And it's planar because all of the atoms are in the same plane. If they weren't in the same plane, well, then there would have to be a lone pair or another bond up here that would repel these away. So if I put another lone pair on it, you'll see that these bonds will bend away from it. So watch. They're just everything's simply arranging itself so that everything is as far away from each other as possible. Now you can go crazy with this. You can add, a crazy amount of bonds to it, but we're limited. Now, it's not that they don't exist, but we're limited for the molecules that we'll be looking at. Standard level chemistry is just 4 pairs of electrons around the central atom. It's kind of fun to play with. Let's do carbon dioxide. So carbon dioxide is 2 double bonds. Again, this is one that I do in the drawings video I'm about to show you. You can see it's linear in shape. Sometimes kids will draw this bent, but the only way it would be bent is if there was another pair of electrons on that central atom to bend it. All right, so I'm going to show you a video here in a minute that shows you how to hand draw these 5 basic shapes in a very simple way. And then you're going to be doing a virtual lab using this very simulator. So you'll be playing around with this yourself. Okay, so let's take a look at how we can draw the 5 basic shapes as simply as possible. Linear. Now, first off, any 2 atom will always be linear. So let's look at hydrogen fluoride. So this would be its Lewis structure. When we draw the shape, we simply remove the lone pairs. This would be linear. Any 2 atom molecule, of course, would be linear. Let's look at another one, another linear shape, and this wouldn't be a 2 atom molecule. This would be 3. Carbon dioxide. So always draw the Lewis structure. That's your key to determine what the shape is. For carbon, it has 2 double bonds. There's no lone pair on the carbon to repel these double bonds anywhere but completely opposite one another. So they're getting as far away from each other as possible. So the shape looks just like the Lewis structure, but without the lone pairs on the oxygens. And you are responsible for the bond angle. And the bond angle here is 180 degrees. Bent. Water is a good example for bent. So you have 2 lone pairs on the oxygen, 2 shared pairs, 2 lone pairs. They all want to get as far away from each other as possible, and they'll do that by taking on a bent shape. Now remember, the shape is only in reference to the bonds. The lone pairs are still there. So these 2 lone pairs are up here, and that's what's repelling these guys away from each other, or away from them, and squeezing them closer together. Now, sometimes students will look at this and say, well, wait a minute, you have one lone pair here, so that would repel these 2 hydrogens down, and then you have another lone pair here, and that would repel it up. So shouldn't they kind of balance each other out? Well, the problem is that you're thinking in 2 dimensions, and that's what's so great about the molecular shape simulator that you're going to be playing around with. You can see for yourself how this will, in fact, have a bent shape. And the bond angle is 104.5 degrees. Let's look at another bent shape, sulfur dioxide. For sulfur dioxide, you have 1 double bonded oxygen and 1 single bonded oxygen, which means you just have 1 lone pair on the central atom. Now that lone pair will repel the shared pairs, just like in water, but there's only 1 of them. So it's not going to repel them away from each other as much as the 2 lone pairs here. So this was 180 degrees, the 2 lone pairs had to go from 180 degrees down to 105.5. But here, you don't have as much repulsive force with just 1 lone pair, so it's not going to repel them down as much. So the bond angle here, the bond angle here is going to be 119 degrees. So it's quite simple. Just remember that if it takes on a bent shape, it's going to have if it has a bent shape with just single bonds, it'll be 104.5 degrees. If you have a double bond, one double bond, it's going to be 119 degrees. And you might ask, well, what if there's two double bonds? Well, if there's two double bonds, that lone pair wouldn't be there, and you would have a shape like this, linear. All right, next. Let's look at trigonal planar. Let's look at boron trihydride. And you might remember that boron is an exception to the octet rule. It'll have only 3 pairs of electrons around it. So each of the bonds want to get as far away from each other as possible, and so it takes this shape. And the bond angle here is 120 degrees, as you might guess. Now it's called trigonal because 3 points of a triangle, but planar is because if you were to look at this with the molecular shape simulator, you'll see that all of the atoms are in the same plane. If they weren't, well then that would mean that the hydrogens are being squeezed closer together than they would be otherwise, and there's no lone pair here for that to occur. Again, the molecular shape simulator you can just immediately see why this would have a planar shape. Okay, let's look at another example. Nitrate. Its Lewis structure is going to have 1 double bonded oxygen, 2 single bonded oxygens, and yes, it would have brackets, a little incidental for our purposes here, but it would have brackets. So the shared pairs around the nitrogen are going to want to get as far away from each other as possible, but there's only 3 of them. So just like with boron, there's only 3. There's no lone pair on the central atom to do anything else, so they just get as far away from each other as possible. The fact that it's a double bond is incidental. It'll have the exact same shape as the one we just did. – 120 degrees. All right. That's trigonal planar. Next, pyramidal. So IB kind of likes it called trigonal pyramidal. So I'll put that in parentheses. I prefer just pyramidal. So pyramidal, ammonia is a good example for that. Draw the Lewis structure. You're going to have a lone pair on the central atom. And all of these pairs, whether it's a lone pair or shared pairs, will want to get as far away from each other as possible, and it'll take this shape. Again, I'm showing you how to draw this as simply as possible. And what you need to understand is that this hydrogen here, you can either think of this as coming out at you or behind you. And you have this one lone pair up here, of course we don't draw it for the shape, that repels these guys closer together. And the bond angle for pyramidal is 107 degrees. And last, tetrahedral. Tetrahedral. Let's look at methane, CH4. Organic molecule, you'll learn about these in our last unit. So when we draw our Lewis structure, everything's at right angles. Of course, carbon's not going to have a lone pair on it anyways. Now, if there was lone pairs on the hydrogens, that's not going to change anything. I suppose I should point that out here. When we're talking about the shape, it's always in reference to a central atom. So that's how we're looking at the fact that we had lone pairs on the oxygens here. That was incidental. That doesn't matter. So the fact that I could have fluorine here, which would have dots around it, and it still would have this as our Lewis structure, carbon bonded to 4 atoms. Now, each one of these bonds are going to get as far away from each other as possible. Now, it's going to be exactly the same like ammonia. You have 3 shared pairs, 1 lone pair. They all want to get as far away from each other as possible. But we don't draw the dots in here. We only draw the bonds. Well, in this case, we do have 4 bonds. So it's going to be exactly the same shape as this, except the lone pair that we didn't draw, because we don't, will now be a bond. And so methane will have 4 bonds to it. And the bond angle is 109.5 degrees. Now, the way that it's drawn here, it looks like this is a big angle and this is a much smaller angle. But again, we're making a very simple drawing of something in 2 dimensions that is in fact 3 dimensions. So this is just a simple way of doing it. The molecular shape simulator that I may have already walked you through, you can see that this would have equal bond angles between all the atoms. All right, so the takeaway here is that if you're asked to draw a linear shape, this is how you would draw it. Replace the atoms. If it was bent with just single bonds, 104.5 degrees. If you had 1 double bond, it would be 119 degrees. Trigonal planar. There'll be no lone pairs on the central atom, and they'll be equally spaced 120 degrees away from each other. It doesn't matter that there's a double bond. Pyramidal. Pyramidal and tetrahedral very similar, except rather than there being 1 lone pair on the molecule, there's no lone pairs. So you can see the similarity between these two. The only difference is that I haven't drawn something off of the nitrogen here, whereas I have here. Now, I should point out that the lone pair here repels a little bit more than the shared pair here. And so the bond angle here is 109.5 degrees, but the lone pair repels these guys a little bit more, so it's 107.5 degrees. So a slight distinction between the two. All right, those are the 5 shapes you need to be able to draw. Okay, your task is now to do the virtual lab molecular shapes. You'll be using the PhET simulator that I showed you how to use. But for now, that is the end of notes.